Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, can I shake hands with the robot? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week we'll be exploring the complexities of designing robot hands that replicate some, or even all, of the intelligent features of human hands. But first, I'd like to remind you that you can send in your questions for my future guests, either by contacting us on social media, we're at Robot Talk Pod on all the socials, or you can submit questions via our website by going to robottalk.org. So, with all that said, it's time for me to introduce this week's guest. I recently had a really interesting conversation with Lorenzo Jamone from Queen Mary University of London, all about robotic hands, dexterity, and the sense of touch. This week, I'm talking to Lorenzo Jamone, a senior lecturer in robotics at Queen Mary University of London, whose work focuses on robot manipulation and the intelligence of the hand. Hi Lorenzo, great to have you on Robot Talk.
Hello, hi Claire, how are you?
I'm good, thanks. How are you?
Yeah, not bad.
So, you're the director of the CRISP research group, which stands for Cognitive Robotics and Intelligent Systems for the People. Can you tell me a bit about what you and your group are working on?
Right, so let's start from the name, right? So there are two things I really like in the name of this group. So the first one is cognitive robotics. So cognitive robotics is basically the reason why I do research, the reason why I got excited about research in the very first place. And the kind of main general idea is that there are two objectives, or let's say two directions. Like on the one hand, we can take inspiration from human intelligence to create smart robots. But on the other hand, we can also use robotic technologies and computational technologies to actually understand more about human intelligence. So in a sense, we can, very generally, we can see this as, for example, psychology, biology, neuroscience contributing to advanced robotics and technologies and artificial intelligence, but also robotics and artificial intelligence contributing to the kind of brain sciences, cognitive science, etc. And this kind of loop really excites me.
Yeah.
And I try to do that in my research and in the research of my students. We do that sometimes, not necessarily all the time we are able to close the loop, but to have that general kind of motivation in mind, for me, it's really important, and I find it really, really exciting.
Mm-hmm.
And I think the second part of the name of a CRISP, Cognitive Robotics and Intelligent System for the People, it's the for the people part, which for us is kind of a constant reminder of why do we do this at all, right? So of course, there is the kind of personal excitement in doing research, but we really want to have an impact on people. And that doesn't mean that necessarily all the things we do have a direct application to something that helps people today and now. Some of it can be more general kind of research that looks at application that may come into 5 or 10 years.
Yeah.
But it's good to have that kind of that idea in mind, and every now and then kind of stop our work and start thinking about, how do we actually use these things to help people? For example, having a robot that help people in everyday tasks, or help our industry to be more efficient and productive and improve the quality of work of people, and so many other areas.
Yeah, it's so important. I love the idea of this kind of feedback loop between, using human intelligence to learn about robots and then using robots to learn about human intelligence. I guess a lot of academic areas kind of try to create models of a system to understand it. And when, you can then compare how the model performs to how the reality is and see what you're missing. I guess it's a similar thing with robots.
Yeah, exactly. So it's like this kind of citation from Robert Feynman, what I cannot create, I cannot understand. So this idea that, if we can build a system, you can, and this is why, for example, robotics in this sense can be very, very useful and very interesting, because of course we can build a computational model of what we think happens in the brain.
Yeah.
But then if we can put this computational model in a robot, and then the robot has to do actions in the real world and do things, then we can have another level of comparison and say, okay, maybe our idea of how the brain works is actually true, or let's say we support that idea by showing that the robot behaves maybe in a similar way to what a human does.
Yeah. You make it sound simple. I'm sure it's not that simple in reality. So one area of your work relates to the intelligence of the hand. And I think most people probably, they find their hands useful, but they don't necessarily think of them being intelligent.
Right.
From my perspective, like looking at kind of, evolutionary biology of how humans evolved, the hand is probably one of the most important features that helped us kind of manipulate the environment around us and come to ultimately dominate the planet. It's complex, it's dexterous, it can move in all kinds of different ways. How hard is that to replicate in a robot?
It is very hard. And I guess that's also the reason why, although, this feeling that the hand is so useful and important, it's quite commonplace, I think, and it has been there since forever. So since they started to create robots, even before like the kind of automatic robots controlled by computers, even like the automatic machines that they were doing from the 16th centuries or earlier. Like I was the other day in a museum in Cambridge, I just saw this mechanical hand from somewhere in the 16th century in Germany. It was kind of a prosthesis, but in fact, it was a mechanical hand with cogs inside that could move.
Ooh.
So, I mean, this idea of like trying to replicate the human hand has been there since forever. And still, like, we are very far from having something that is even remotely similar to our hand, both in terms of, let's say, the mechanical or electronics engineering, but even more so in terms of the actual intelligence. So the computational aspects of how do we combine the perception, so the visual and tactile perception with the movement of the hand, and put this together in order to do the amazing things that we do every day without even thinking, right? So the way we use our hands every day, it's amazing. And sometimes we, let's say, simply pick objects, which again is already difficult if you want to try to replicate that in robots, especially if you want to do it, I don't know, in a messy kitchen or in a place you have never seen before with objects you never touched before. It's already quite difficult. But sometimes we do even more sophisticated things when we do so-called in-hand manipulation. So we have an object that we are holding in our hand and we move that object. For example, if you write with a pen, right, you are holding your pen within your fingers, and the pen should be stably held within your fingers. But at the same time, you are moving this pen around and actually writing something, so a very precise trajectory. So it's an incredible level of sophistication. Of course, we never think about it because our let's say our brain is so much dedicated to using the hands that for us it comes simple. But it's in fact very difficult. I mean, a very big portion of our brain is dedicated to controlling the hand.
Yeah. And of course, it still takes us a long time to master it, right? Like time spent learning hand-eye coordination and if I think about all the time I spent at school learning to write, like handwriting and all of those things, it takes us a while to master it.
Of course, yes. I mean, I think the level that we have nowadays of robotics, it might be comparable to, I don't know, maybe a 1-year-old or something. I mean, we are really far from getting to kind of adult level of dexterity that we have in humans to have something similar in robots.
Yeah. So when you say the intelligence of the hand, is that what you mean, the way that the brain and the hand are so closely interlinked?
Yeah, I mean, in general, I think this is, let's say, for our team, as you introduced, like, let's say, we have this cognitive robotics idea, and that's more kind of a driving thought, like a driving motivation. But then more operationally in our research, we focus on intelligence of the hand, and by that I mean simply all the smart things that you do with your hands. We try to somehow explain them, replicate them in robots, create computational model that would, let's say, describe them and implement them. And this goes from, of course, picking up objects and manipulating objects, like I just said before. And in that respects, we focus a lot on the sense of touch, which is incredibly important for that.
Yeah.
But we do also studies in, let's say, looking at how do we use our hands in other situations. We use our hand to communicate with others.
Yeah.
Use our hands to, for example, improve our perception of other things, like, for example, music perception. If you're listening to a song and you're trying to understand the rhythm of that song and try to maybe play along or sing along, you maybe tap your hand. You tap your hand to keep the rhythm, right? And there are, again, very sophisticated processes that in which our brain decides when exactly to tap in order to help the music perception, so the auditory perception. And these are just a couple of examples, but there's really like a huge world of smart things that we do with our hands. So when I mean the intelligence of the hand, I mean that all these smart things that we do, and somehow they fall within the remit of the research that we do in my team. And of course, we don't do everything about it because it's it's huge, but several things we do in that respect.
Yeah. So is the idea to ultimately to develop one robot hand that does all of these things in the way that our hand does, or are you trying to kind of pick the particulars for different tasks, if you see what I mean?
Yeah, I mean, of course. So with our hands, we do so many different things, right? And so it's clearly like also very good hardware. So ideally, maybe in the future, we could really have a robotic hand that look maybe similar to our hand, not necessarily the same, but we may have a kind of a general purpose robotic hand that could do so many different tasks. I think we are very far from that, even in understanding exactly how this hand should look like, right?
Yeah.
So at the moment, I think it's more to focus maybe on specific aspects and try to understand some of the, let's say, the important factors behind to understand why our hand works so well, and then use some of those ideas to create robots, right? So, for example, I don't know, there is also, like, if you also think like traditional robots, they are made of hard materials.
Yeah.
So metal, etc. Right. And then if you look at our hand, it's a combination of hard and soft. We have hard bones, but then we have also soft skin covering the hand. And for example, if we create hands that have maybe a hard part, which is somehow easier to control the movements of, but then with a soft layer outside, similar to a skin, even just by being a soft layer, that already helps to manipulate objects, because the hand could kind of more naturally conform to the shape of different objects. And then in addition, you can go beyond. You can add sensors, for touch sensors, for example, in this soft layer, and then you have the combination of both having a soft interface, but also an interface that allows you to measure the contact forces and understanding properties of objects and interact gently with the environment. So, and then, for example, you can have this around the hand, let's say covering a hand that looks like the human hand, or you can have a similar thing covering what we call in robotics like a robotic gripper. So, which is a much simpler type of hand that can just open and close, right? You have two faces that they close on top of each other. So, of course, that's nothing similar like a hand, but we can maybe have that with a soft sensor on top, and already we make manipulation much easier by using this kind of idea or inspiration.
Hmm. Cool. Yeah, it sounds like a fascinating area to work on. And one area that you're kind of applying this to is robotic manipulation in advanced manufacturing. And this project aims to teach robots how to handle objects like humans do. So, how are you approaching this?
Yeah, so of course in manufacturing there are many situations where we want a robot to pick objects and move them around in industry. One area that we are looking more closely to is kind of food manufacturing or food logistics. So in
Mm.
general, those areas where you have a robot or typically a person nowadays will have to manipulate and pick and place food, fruits, for example. So things that are delicate and also deformable, so a bit more difficult to handle,
Mm.
rather as opposed to, for example, rigid objects, rigid parts, for example. And so there again, a sense of touch is very important,
Mm.
but also it could be important to understand what are the strategies that a person uses in order to manipulate these complex objects, let's say.
Yeah.
And one strategy that we are investigating at the moment is to use a teleoperation. So by teleoperation, I mean that there is a person that will move its own hand, and
Mm.
by moving the hand, the movement will automatically be transmitted to a robot, and the robot will do exactly the same movements. And in addition to that, we also have technologies that allow us to give feedback from the robot to the user. So when the robot touches something, the user will feel this touch of their own
Mm.
hand. And we have different ways in which we can do that. And if you have this kind of system, then you can have the human person will teleoperate this robot. So it will do, let's say, picking objects and moving objects around, but not using their own body, right? They will use the robot body.
Yeah.
So somehow it's a way to transfer the human intelligence, or let's say the human intuition,
Mm.
into how to handle objects to the robot in a way that is then feasible for the robot to replicate. Because if we were simply looking at how people pick objects with their own hand, then we have the problem of translating that to a different hardware, basically.
Right.
While if
Yeah.
we have the person directly using the robot, then we can have a more direct way of using the intelligence of the person. And so the idea is that in a first phase, you may have the person that teleoperates the robot directly,
Mm.
maybe choosing different type of objects, etc. We can collect data, and then using that data, we can use AI techniques for the robot to learn. So let's say to remember what has been done by the person and to apply this to new situations.
Mm. That's a really interesting way of doing it. Yeah, like making the person translate it to your hardware, basically.
Exactly. So we kind of exploit a bit more the intelligence of the person, the ability we have to even kind of generalize our intelligence to a different body.
Yeah. Cool. And then, yeah, another area you're applying your work to is the nuclear industry. And this idea of teleoperation is used a lot there, obviously, because they have places that are radioactive and people can't go into. So how easy is it to transfer these kinds of technologies from one industry to another?
Yeah, so some of the ideas, as you mentioned, like this idea of teleoperation, it's also very common in the nuclear industry, and so I mentioned, let's say, one way in which you can use teleoperation, which is the idea to kind of transfer the human intelligence to the robot.
Mm.
But we also use teleoperation, let's say, simply to operate a remote robot.
Yeah.
And this we do it in many situations because ideally in the future we will have autonomous robots that you can take a robot, put it in a challenging environment, for example, a nuclear power plant where there are radiations, you don't want to have people there, right?
Mm.
So you can take the robot, put it there, and then the robot will be autonomous, then do whatever we tell them to do, right? But we are still not there, right? So in many cases, we use the teleoperation as a way to, again, use a little bit more the intelligence of the person who operates the robot. And in the nuclear industry, so we had a big project here in the UK about like using robotic technologies for nuclear decommissioning. This was a huge project with several universities and several companies involved. And this is because let's say decommissioning these nuclear facilities is something that it's very costly in general. So the UK is trying to find a novel technology to do that better and quickly, more quickly. And yeah, so for example, I didn't know much about this kind of the problems of the nuclear industry and nuclear decommissioning before I started this project. And so one thing that I found very interesting and also a little bit scary is that there are these, so in some of the nuclear facilities that they're not operating anymore. So that we still have high radiation environments there, for example, in Sellafield in the north of the UK. They have some of these kind of storage buildings where they have stored nuclear waste.
Yeah.
And which is radioactive, and these buildings are completely closed, completely sealed, because you don't want, of course, anything to go out from there. But the point is that in many cases, they don't really know what's inside and what's the status of the things inside, because they've been closed for many years.
Yeah.
And so there are projects where we try to use a robot to go inside there, and one approach is to open very small holes in the walls. And then go inside with soft robots that are, let's say, kind of a snake robot, you can imagine, that will just go inside this. And then when it's inside, of course, first it will do some measurement of the radioactive levels, but also trying to understand what's inside.
Yeah.
And one problem there is that it's very hard to use several electronic components, because if the radiation levels are too high, the electronic components will not work anymore. So you may go initially with a camera, but it could be that the camera, after a few minutes, it doesn't work anymore. So we tried also to use other sensors, for example, tactile sensors, because we can make some tactile sensor where we don't really need to put electronics on the sensor itself, where we can put the electronics outside, let's say, so far from the sensor. And then imagine with this snake robot, we can go inside and look for as long as the camera works, but then start touching and have tactile information. So we can use that to explore the environment and, for example, understand if the walls are okay, or if there are cracks in the walls. So if there is a risk of the building collapse at some point, or if there are like barrels with the nuclear waste, whether they are intact or whether there are defects. So kind of explore and monitor and map the space. And this problem, for example, they're quite specific to the nuclear environment because of the levels of radiation, where some of the electronics and some of the components may not work.
Yeah. All of this is making me think of the TV series Chernobyl, where they try to send the robots in and they just stop working.
Yeah, exactly like that.
It makes me wonder, though, if you could use... I've spoken to some people who make like inflatable robots that use kind of pneumatics.
Pneumatics. Yes. Yes. Yeah. In fact, the robots we use for that are exactly based on that concept or similar concept. But this is not necessarily. So that part of the robot, like inflatable robot, is not necessarily my research, but is research that colleagues of mine they do in the team. There's Professor Althofer, Kaspar Althofer, for example. He works a lot in this area. And yes, those are exactly how it works. They will inflate, and then so they will be small, and they can pass through this narrow opening in the wall, and then they will inflate and become a bit bigger and more. They can be maneuvered inside.
Yeah. Cool. I always think it's cool in robotics that, like, you start off working on one thing, I want to make a hand. And then suddenly you find yourself working at a nuclear power plant. Like, it's so... Yeah. I don't know what the word is. It's so kind of diverse in the areas you can apply it to.
But then, of course, like I mentioned this problem, but then otherwise, some research that we do in my team is more generally about manipulating objects with the hand and with grippers. There are other situations in power plants, but also in other challenging environments where you maybe don't necessarily have such a high level of radiation, so you can have electronics there. But you still like kind of have mid levels of radiation. You prefer not to put a person there, right? And the same is, you want to explore the deep sea, you want to explore the surface of Mars. I mean, those situations can be like potentially harmful for a person or not necessarily comfortable. And one challenge there is where you may want to manipulate objects, but you have absolutely no idea what type of objects you will encounter. So this is very different from, for example, the industrial manufacturing, because in a company, you may have at least some ideas of the objects you will have to manipulate, so you can use that information to make your system. While in this other situation, you have absolutely no idea of, you're going to pick some rocks, how heavy they could be, what is whether they're going to be slippery or not. So you have absolutely no idea of the type of objects you may encounter. And so something we work on is really have technologies for robotic manipulation where we do not make any sort of assumptions about the objects that we are going to manipulate. And again, if you think for humans, this is relatively easy because we are so good at generalizing. Maybe we learn how to pick and manipulate certain objects, and we find a new one we never used before. We are very quick at transferring that knowledge to new situations. But for robots and even artificial intelligence technique, this is still very, very difficult. It's a big challenge.
Sure, yeah. Lorenzo, it's been great speaking to you today. I've been chatting to Lorenzo Jamone, a senior lecturer in robotics at Queen Mary, University of London. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please do share the podcast, subscribe, and leave a review to let us know what you think. And make sure you check out our social media channels to see a photo of a robotic hand that Lorenzo has worked on, opening a bottle. We're at Robot Talk Pod on all the socials. And don't forget to enter our t-shirt competition for a chance to win your very own Robot Talk t-shirt. All you have to do is share your favourite episode on social media and tag us at Robot Talk Pod. Next week, I'm chatting to Fionn Llewellyn from Ocean, all about seafaring robots and ocean sensing. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.